Has science finally cracked one of the most perplexing riddles in modern cosmology? For years, experts have puzzled over why the universe appears to be expanding at a rate much quicker than our most trusted theories have anticipated. This mysterious mismatch between observation and prediction has been dubbed the Hubble tension, and it's kept astrophysicists scratching their heads for decades. But now, a team of researchers from the University of Bonn and the University of St. Andrews believes they may have stumbled upon a clue that could shift our entire understanding of the cosmos. Their breakthrough points to the possibility that our home galaxy, the Milky Way, isn't located in an average patch of the universe as previously assumed. Instead, it might be positioned within a vast, unusually empty region of space, a cosmic void that spans enormous distances and contains far less matter than typical parts of the universe. What's even more fascinating is that when this idea is combined with an alternative approach to gravity, one that doesn't rely solely on the traditional framework of Einstein's general relativity, the mismatch between what we predict and what we observe seems to disappear. But there's a catch. Accepting this possibility would mean challenging the very core of the standard model of cosmology, which has served as the foundation of our understanding for nearly a century. Such a proposal doesn't just tweak the details, it rewrites the rules, potentially triggering a seismic shift in how we interpret the universe's behavior. Roughly 100 years ago, scientists believed space was still and motionless, with no grand-scale changes taking place. That was the accepted view for generations. Even Albert Einstein, widely regarded as one of the greatest scientific minds in history, initially clung to this belief. When he crafted his equations for general relativity, he realized they predicted a universe in motion, something he didn't believe at the time. So, in an effort to maintain the idea of a stable universe, he introduced a term called the cosmological constant to counterbalance the predicted expansion. Later in life, he admitted that this addition had been a serious misstep, calling it the biggest blunder of his career. However, another thinker, Belgian priest and physicist Georges Lemaître, had already taken Einstein's equations and run with them. In 1927, Lemaître demonstrated that the equations naturally led to a model of an expanding universe. Unfortunately, Einstein dismissed this insight as little more than a mathematical trick, not realizing that Lemaître was pointing directly at a truth that would soon reshape our cosmic view. In hindsight, it's clear that Lemaître was ahead of his time. His model didn't just stay within the realm of numbers, it made a bold prediction that could be tested through observation. He argued that if the universe was indeed expanding, galaxies would be drifting away from each other, much like dots drawn on the surface of a balloon that stretches as air is blown into it. Not only that, but he also predicted that as these galaxies moved farther away, the light they emitted would become stretched, shifting toward longer wavelengths and appearing redder, a phenomenon now known as redshift. This prediction found strong confirmation just a few years later when Edwin Hubble, an American astronomer working at the Mount Wilson Observatory in California, collected meticulous data on the light from distant galaxies. He observed that almost all of them exhibited this redshift, offering solid proof that the universe was not only expanding, but doing so consistently in all directions. This discovery marked one of the most important moments in the history of astronomy, paving the way for the Big Bang theory, which proposes that everything began from a single, unimaginably dense point that exploded outward to create the cosmos as we know it. But the surprises didn't end there. By the 1990s, using new observational tools and data, astronomers made yet another shocking discovery. Not only was the universe expanding, but the speed of this expansion was increasing. In other words, galaxies weren't just moving apart, they were doing so faster and faster over time. To explain this strange behavior, scientists introduced the idea of a mysterious force known as dark energy, a powerful yet invisible agent that seems to oppose gravity and push the fabric of space itself outward. While dark energy remains one of the most enigmatic concepts in modern science, its inclusion became essential to explain why the universe's expansion was accelerating instead of slowing down. This brings us back to the heart of the Hubble tension, a discrepancy that raises a very basic yet troubling question. Why are our modern measurements of the expansion rate faster than what theoretical models predict? At the center of this dilemma lies the challenge of calculating the universe's current rate of expansion, a value known as the Hubble constant. In theory, we should be able to determine this figure with great precision, but in practice, the results vary depending on how it's measured. The tension comes from the fact that there are two primary methods for estimating the Hubble constant, and they don't agree. One method, based on the standard cosmological model and data from the early universe, suggests a value of about 67 kilometers per second per megaparsec. To put that into perspective, a single megaparsec is roughly equivalent to 3.26 million light-years, and one light-year spans about 9.46 trillion kilometers. This means that, according to this model, for every additional 3.26 million light-years of distance, galaxies are receding at an extra 67 kilometers per second, translating to an astonishing speed of around 244,000 kilometers per hour for each megaparsec. But here's where things get complicated. Direct measurements of cosmic expansion using techniques like observing supernova, gravitational lensing, and variable stars like Cepheids or red giants produce a significantly higher value for the Hubble constant, about 73 kilometers per second per megaparsec, which translates to an even faster speed of around 264,000 kilometers per hour. This creates a difference of approximately 20,000 kilometers per hour between the two values, a gap that current models struggle to explain. How can two reliable measurement methods result in such drastically different outcomes? Is this evidence of a flaw in our understanding of the universe? Or could earlier studies have unknowingly incorporated measurement errors that skewed the results? These questions lie at the heart of the ongoing Hubble tension debate and continue to push scientists toward new and sometimes controversial theories. This pressing question, why the universe seems to be expanding faster than theory allows, was recently revisited with the help of one of the most powerful tools ever built for observing the cosmos, the James Webb Space Telescope. With its unprecedented ability to capture high-resolution details from deep space, Webb provided scientists with an entirely new perspective on the ongoing Hubble tension. Leading the charge was Nobel laureate Adam Rees from Johns Hopkins University, whose team took a fresh look at 2 years' worth of Webb's data and compared it to previous observations made by the Hubble Space Telescope. Thanks to Webb's vastly enhanced capabilities, which many researchers liken to switching from standard to ultra-high-definition viewing, this newer data didn't just confirm previous suspicions, it sharpened them. What emerged from this rigorous analysis was one of the clearest confirmations yet that something doesn't quite add up. Webb's observations spanned a variety of celestial phenomena, including exploding stars known as supernova, flickering variable stars, luminous red giants, and rare carbon-rich stellar giants. Together, they painted a consistent picture. The universe is not behaving according to expectations. The most recent calculations based on Webb's observations pinned the Hubble constant at 72.6 kilometers per second per megaparsec, a figure that once again contradicts predictions from the standard cosmological model. According to Rees, this growing discrepancy between what we observe and what theory predicts suggests that something fundamental is missing from our current understanding of the cosmos. Perhaps, he speculates, some overlooked ingredient in the early stages of the universe gave an unexpected surge to its expansion, like a hidden booster rocket in the wake of the Big Bang. Or maybe the mysterious force we call dark energy isn't static after all. What if it's changing over time, becoming denser, stronger, or more dominant as the universe ages? These are tantalizing possibilities, yet they still fall short of explaining everything. That's why some researchers are now turning their attention toward more unconventional theories, ideas that look beyond dark energy and question the very nature of space and gravity itself. One especially thought-provoking hypothesis proposes that our entire galactic neighborhood, including Earth and the Milky Way, could be situated inside an enormous structure called a supervoid. To grasp what that means, we first need to take a step back and look at how the universe is organized on the largest scales. Most people are familiar with the idea that stars group together to form galaxies. These galaxies, in turn, often cluster together into larger formations called galaxy clusters, and these clusters can form even larger patterns known as superclusters. For a long time, scientists believed that these superclusters represented the biggest coherent structures in the universe. But then came deep space surveys that revealed an even more fascinating cosmic architecture. These surveys showed that superclusters aren't randomly scattered throughout space. Instead, they are arranged in an intricate web-like pattern. This enormous lattice, often called the cosmic web, is made up of long, thread-like structures known as filaments. These filaments can stretch for hundreds of millions of light years and act like the scaffolding of the universe, connecting galactic regions across vast distances. But the filaments don't just form a solid network, they also frame enormous, bubble-like regions that contain very little matter. These empty pockets, known as voids, span unimaginable volumes of space. And although when we gaze into the night sky it appears densely populated with stars and galaxies, many researchers now believe that the universe is largely made up of these vast, barren regions. In fact, some studies suggest that anywhere from 50 to 90% of the cosmos is composed of these cosmic voids, enormous expanses where the density of matter is shockingly low. One study led by Sergei Malikov from the University of Bonn, conducted in collaboration with scientists from the University of St Andrews in Scotland, puts forward the idea that these voids may be more than just empty space. They could be a missing piece in the cosmic puzzle surrounding the universe's accelerated expansion. Their research introduces the idea that our own galaxy might be located in one of these underdense regions, much like an air bubble trapped inside a sponge or cake. And because the space around this bubble contains more matter, the gravitational forces are stronger on the outside, effectively pulling surrounding galaxies toward the outer edges of the void. This creates the illusion that those galaxies are moving away from us more rapidly than expected. This simple yet powerful concept offers a potential explanation for why measurements of the Hubble constant appear higher when taken from our local region. If the area we inhabit is less dense, then nearby galaxies would seem to recede faster simply because we're sitting inside a gravitational dip. It's a subtle but important distinction, and one that could significantly influence our interpretation of cosmic expansion. However, there's a problem. The standard model of cosmology doesn't include the possibility of such large local voids. It operates under the assumption that matter is evenly distributed throughout space on large scales, leading to a more uniform expansion. But if that's truly the case, how do we explain observations of galaxies more than 600 million light-years away, galaxies that are moving away from us at speeds far beyond what current models can account for? This is where new ideas about gravity come into play. Pavel Krupa, who contributed to the supervoid study, explains that the standard cosmological model relies heavily on Einstein's conception of gravity as outlined in the theory of general relativity. But what if gravity doesn't behave the same way everywhere, especially on cosmic scales? What if the force of gravity evolves under different conditions than we've assumed? To explore this, the researchers turn to a modified approach called modified Newtonian dynamics, or MND for short. First introduced around 4 decades ago by Israeli physicist Mordechai Milgram, MND challenges some of the core assumptions of general relativity and suggests alternative behaviors for gravitational forces in low-density environments. Though it remains a fringe theory in the scientific community, MND makes some very specific predictions, among them the existence of massive, empty voids scattered throughout the universe. This, it turns out, is the crucial link. If Milgram's vision of gravity is closer to reality than Einstein's on these grand cosmic scales, then much of the confusion surrounding the Hubble tension could be resolved. In fact, simulations using MND-based models show that these large underdense regions would naturally lead to accelerated expansion rates similar to what we observe. In essence, by tweaking our understanding of gravity, the whole puzzle begins to make sense. Galaxies would appear to move away faster, not because of some mysterious force or measurement error, but because the structure of space itself and the forces that govern it are far more complex than we ever imagined. The tension in that case wouldn't be a problem to fix, but a signpost pointing us toward a deeper, more accurate theory of how the universe really works. If these unusual observations can truly be traced back to uneven concentrations of matter across the universe, then in theory, there would be no need to propose multiple different expansion rates for different regions. Instead, everything could be explained by a single universal expansion constant. Such a unified explanation, however, comes with a massive trade-off. it would require letting go of some of the most trusted and foundational ideas in physics, specifically the classical models of gravity developed by Isaac Newton and later refined by Albert Einstein. These theories have underpinned modern physics and astronomy for centuries, shaping how we understand everything from falling apples to orbiting planets to the motion of entire galaxies. To suggest that they might not fully apply on cosmic scales is to question a legacy that has long been considered unshakable. Astrophysicist Pavel Kruper recognizes just how steep a challenge this presents. He points out that deeply rooted scientific theories don't just guide our understanding, they also influence which ideas are taken seriously and which are pushed aside. In the world of scientific research, these long-accepted frameworks often serve as gatekeepers for resources, especially when it comes to funding. Because Newtonian gravity and Einstein's relativity are so widely accepted, most research committees tend to favor projects that operate within these established paradigms. As a result, any theory that dares to challenge these cornerstones, no matter how compelling or well-constructed, may be labeled as fringe or speculative, making it extremely difficult for researchers to obtain financial backing or institutional support. Krupa emphasizes that this deeply ingrained preference for traditional models can slow down the process of scientific discovery. When alternative ideas are dismissed outright, not because of flaws in the data, but simply because they don't fit within the conventional mold, opportunities for breakthrough insights may be lost. The scientific community, like any other field, is influenced by human behavior, by reputation, by tradition, and by the cautious nature of academic institutions. This means that even bold, innovative theories that might eventually reshape our understanding of the universe can struggle to gain traction in their early stages, especially when they challenge the legacy of giants like Newton and Einstein. Oh, and speaking of acceptance, here's a bit of lighter news. It looks like our committee just approved your complimentary subscription. Welcome aboard. We're glad to have you as part of this ongoing exploration of the universe's greatest mysteries.